Hello everyone. This is the second video from the COMP382 language, machine and computation that I usually actually call it theory of automata. So in this video we are going to cover chapter 1 of your textbook. I'm going to discuss about some, defining some terms that we refer to them a lot in this course, and then I'll just give a review of formal proofs, different form of formal proofs, because in this course we are going to actually use many of those form of proofs. Okay, the very first concept is alphabet. An alphabet is going to be a finite, non-empty set of symbols. We use the sigma to show the alphabet, this Greek alphabet. For example, as the definition tells you, an alphabet is a finite, non-empty set of symbols. For example, the binary alphabet is going to be only two symbols, 0, 1. You can actually define any set of symbols as your alphabet. For example, all lower level English letters alphabet, and or for example alphanumeric alphabet, which is going to cover all the lowercase and uppercase, and also including the 10 digits 0 to 9. Or for example the set of all ASCII characters, or a set like ACGT, which is going to be the set of DNA molecule letters. For example, A and B as a alphabet, as your alphabet. So you can define your alphabet to be anything, any finite set of symbols. But this is important that your alphabet cannot be infinite. All the symbols in your alphabet should be clear. Okay, so over an alphabet, we can define a word or a string, or sometimes a sentence, we call it a sentence, to be a finite sequence of symbols that all those symbols are from the given alphabet. For example, the string X is this string 0101. As you can see, this is a sequence of 4 symbols. All the symbols are coming from this alphabet. I don't have any other symbol in this sequence, and that's it. This is a valid string, and the length of it is finite. I know that this is 4 symbols, and it is a valid string over this binary alphabet. We also would define an empty string and call it epsilon. Be careful, empty string is not, although we are using the symbol epsilon, but actually what we are referring is a string that doesn't have anything, nothing basically, okay? But it is a string. You can actually just think about it as an empty string in, just to get the idea. Think about it as empty string, for example, when you are writing in Java, any programming languages, a string which the length of it is 0 and it is empty. But there is still something, right? That is a string, but it doesn't have any character. So we define the length of the string, any string like W, by actually putting it in 2 pipe character, and this is going to be the number of symbols in the string. So if your string is epsilon, the length of that is going to be 0. Okay, epsilon is an empty string. Okay, we define an operator concatenation over the strings. The concatenation of 2 strings is just like you put, for example, x, y, is going to be the concatenating all the symbols of x to all the symbols of y, and the order is important when you write it as xy. So all the symbols of x comes first, and then at the end all the symbols of y will be concatenated to that, and you don't add any other character in between, or you don't put a space or anything. So it's just going to be a new string. If x and y, both of them have been defined over the same alphabet, the result xy is going to be defined over the same alphabet, because all the characters or the symbols are coming from the same alphabet. Just one thing, that epsilon can be concatenated to any string, and the result is going to be the original one. So it doesn't matter if you concatenate the epsilon first or concatenate it at the end. The result is going to be the same, the original string. So you can think of it as very similar to, analogous to 0 in addition. So epsilon is identity for concatenation in strings, just like 0 is identity for addition. So when you are adding 0 to any number, the result is going to be the same, the original number. Another notation that we will use a lot is powers of alphabet. Just assume sigma is an alphabet. We can actually define a set of some strings of a specific length by putting power over sigma. So formally we define sigma power k to be the set of all strings that strings have been generated from the symbols of inside the sigma, and the length of all of those strings is fixed k. For example, if I have a binary string, alphabet, so sigma 2 is going to be the set of strings that define over binary alphabet, and the length of all of those strings is 2. So it's going to be 0, 0, 0, 1, 1, 0, and 1, 1. Only this set of strings, nothing else. So sigma power 2 is in fact a set of strings. It is later on we will actually just define it. This is going to be a language. Or for example, sigma 3 is going to be the set of all strings, all binary strings of length 0. So it's going to be 8 different strings. So I'm not going to write all of them, but anyway, you know that this is going to be 8 different strings. So here we can define power 0 as well. If you use actually power 0, you are actually saying that the set of all strings of length 0. Basically, it doesn't matter what is the alphabet, always sigma 0 is going to be the set of only epsilon. Okay, regardless of what is sigma, if it is the set of all English letters, binary digits, 10 digits or whatever, the sigma power 0 is going to be only one string, the set of one string, which is epsilon. Just one more thing here is that when we defined actually these powers, you can see that sigma power 1 is going to be all the strings of the length 1. So whatever is the, for example, if sigma is a binary alphabet, sigma power 1 is going to be the set of these two strings, 0 and 1. But you should be careful. Although they look very similar to each other, but they are not the same because the type of them are different. This is an alphabet. This is a set of languages. Sorry, a set of strings. So they are conceptually different, although they look the same. two other notations that we have here is um, sigma star. Sigma star is going to be the union of all powers of sigma. So, this is going to be the set of only empty string epsilon. This one is going to be, for example, if your alphabet is binary alphabet, this one is going to be this strings of length 2, and so on. So the union of all these are going to be represented as sigma star. And this is important for us because sigma star basically tells us the set of all possible strings defined over the alphabet. Think about it, the set of all possible strings that can be generated using the symbols in alphabet. Sometimes we wanted to actually exclude epsilon. So you can see that because epsilon belongs to sigma star, sometimes you might actually wanted to exclude that. So that's why we also define this notation that sigma plus, just the same as sigma star, just it excludes epsilon. So basically the set of all strings of length at least 1 over a specific alphabet. So you can actually write sigma star to be sigma plus union the set of empty epsilon, empty string or epsilon. So the next term that we refer to a lot is languages. So a language is defined over an alphabet, and we say that L is a language over alphabet sigma if L is a subset of sigma star. So basically, L is going to be a set of strings from that can be generated by sigma, all the symbols in sigma. So it actually summarizes it in this way because sigma star is basically the set of all possible strings over sigma. So when you write it as L is a subset of sigma star, you are actually just basically saying that yes, this is going to be a set of strings, but we don't know which string. So each language will have some other specification. For example, let me actually just give some examples of the languages. Assume your alphabet is, for example, the English alphabet. So one language will be, for example, English itself, right? So English is a language defined over the alphabet of English. Or for example, the C or Java or Python or all other programming languages are are a language defined over the an alphabet which includes which actually covers all the lowercase, uppercase, digits, punctuations, and mathematical symbols, right? All those symbols, basically all those symbols that you have over your keyboard. That is the alphabet, and the language is, for example, C or Java. And you can see that, for example, Java is a language, right? And all the valid programming language, all the valid code, source codes that you can write in Java or C++ is going to be, a part of that language. If you have a sequence of letters which is not a valid source code of Java, that doesn't belong to that language, right? So if there is a syntax error, that doesn't belong to that language. Languages are important for us because they are going to represent the problems. In this course, although actually the definition of a language is general, just like this definition that these examples that I gave, but basically in this course, most of the time when we are talking about a language, we are referring to some, a smaller alphabet, like the binary alphabet or the alphabet of for example, two letters A and B, or for example, A, B, C, or something like this, some very abstract, actually, alphabets and corresponding to that abstract languages. For example, the language of all strings consisting of n number of zeros followed by n number of 1. So this is going to be all the strings that has n number of zeros, including zero number of zero, following by n number of ones. We also actually represent such a language in this format as well, that 0 power n, 1 power n. So this is just a representation for the same language. Or for example, the set of all strings with equal number of zeros and ones. So you can see that all these are our different examples. And this, you can see that this is infinite, this is infinite set, this is also infinite. The set of all binary numbers whose values is a prime number. So for example, this represent 2, this is 3, right? This is 5, this is 7, 11, and so on. Some actually facts about the languages. Sigma star itself is a language over any alphabet, okay? Basically because it is the set of all possible strings, and it is a set, so basically sigma star is a subset of itself as well, right? Empty language, don't confuse it with empty string. Empty is a language, is a valid language. It basically is a set that doesn't have any string, okay? So nothing is inside this language. So MT is also a valid language over any alphabet. The language of one string epsilon is also a valid language over any alphabet. And be careful, this is not equal to the set empty. The set empty doesn't have any string, but this one is a language that has a one member, and that is an empty string. So they are different. Empty set doesn't have any member, okay? Any item, nothing. So when we are defining a language over an alphabet, we didn't really put any constant over the language. The language can be infinite number of items. The only actually constraint is that all the strings should actually generated from the given alphabet, and the alphabet, the possible symbols that you can use to generate the strings should be finite, should be fixed number of symbols. Otherwise, other than that, there is no other constraint over the language. Okay, let's actually just come back to the membership problem and the fact that in this course, always when we talk about the languages, basically we are talking about a problem. All the problems represented as a language. So in theory of automata, a problem is formally defined as given a string W. So a problem will be actually represented using a language, and the problem that you are solving it is in fact a membership problem. That is saying given a string W belongs to generated from an alphabet sigma, and a given language L, again over the same alphabet, you should check whether W belongs to L or not. So this is something that you solve, and which is basically a membership problem. You just check if W belongs to L, W is in the set of strings L or not. L is a language, and we just wanted to see that W belongs to that or not. For example, assume L is a language of strings that has equal number of zeros and ones. Okay, so given a string W like this, we wanted to check if W belongs to L or not. So if it belongs to L, you return yes, otherwise you return no. So every problem that you solve, for example, you should think about it in this way, that in a regular basis, this problem for you would be just like this, that okay, someone give you an string and you would check if it has this equal number of zeros and ones, right? But in theory of automata, it is just to check that it W belongs to the language of all the strings with equal number of zeros and ones or not. If it doesn't belong to that language, you return no, and the answer of that problem is no. So, as I've mentioned a couple of times so far, any problem in computer science basically is a membership problem. We can represent it as a membership problem. Let's actually see some other examples. For example, that famous example of prime number. You wanted to check if a number is a prime number or not. In the membership representation, it is just like you have a language, which is the set of all binary numbers, whose value is a prime number. So given a binary string, you wanted to see that if this string belongs to this language or not. If it doesn't belong, so it means that that is not a prime number. Or for example, when you are compiling, just assume that you wanted to check if a given file is a valid C code or Java code or whatever programming languages or not. So basically your language here, don't be confused with the programming language. The language here is going to be the set of all valid codes written in C, okay? And your input is actually a sequence of characters. You wanted to see that if this sequence of characters, this string, basically belongs to that language or not. If there is no syntax error, it means that it belongs to that. If there is syntax error, it doesn't belong. So basically this is the task of a compiler. Although you know that the compiler does more than that. Not only it checks if it belongs to the set of all valid C source codes. It also actually just, if it is not, it finds the syntax errors. If it is, it also actually compile it, convert it to a object file, and so on. So this is also, in fact, a membership problem. The first part of this course, which is going to cover a couple of weeks, is finite state automata. And basically when you're actually talking about the theory of automata, or finite automata in this, at the first part of the course, they in fact has a lot of actually applications in real world. This is not just abstract notation to just do some proofs or just doing this course. No, it has definitely way more applications in software and hardware. For example, any compiler has 4 different phases. The first phase is, we call it actually a lexical analyzer, and in fact that phase is a finite automata. So you don't know what is a finite automata, so I don't want to actually make it very complicated here. I just wanted to say that this is not only some abstract definition, which is just for proving something or just covering this course. It has way more applications. So what is a finite automata? What is a finite automaton? It is a finite automaton is going to be, um, you know, any machine that has a couple of states and some transitions that your machine at each step is going to be in one of those states, and by actually applying any of those transitions, you just go to another state. This is going to be a finite automata. A very simple example is going to be, for example, all the switch on and off switches that you have. For example, the one that you use for your light, the one that you use for any machine that you have is going to be a finite automata. It has two states, right? On and off. If you are in off state, if you push the switch, it actually goes to the state on, and if you push it again, it goes to a state off. So it is exactly the definition of a finite automata. You have a finite number of states and some transitions, and the machine at each step is going to be in one of those states. So you have a couple of actions and a couple of states. Let me actually just show you a little bit more complex example. Just assume that you wanted to, for example, write a pattern check, something actually to check a pattern like then. Okay, you wanted to see that if you wanted to go over a string and check if there is a pattern then inside this string or not. You can in fact create a finite state to do this. Your machine is going to have 5 different states. At the very beginning, you will be at the state that you haven't recognized anything. If you see the letter T, your machine will, you actually read the whole input string, and if you see the letter T, you go to another state that actually basically tells you that you just saw a character T. And if you see H, you will go to another state that tells you that, okay, I just saw the 2 letters T and H. If you see E, you go to another state T that tells you that you have seen the T, H, E. And if you see N there, you go to these states. So this is a finite state automata. It is not complete because it doesn't actually show all the transitions, but I just abstracted away all of and remove all of those transitions to make it very simple to understand here. So any finite state is going to be a set of states, a finite number of states, a couple of transitions between them. If actually you are implementing some finite state that basically represent a membership problem. So one of those states, at least one of those states should be a final state to show that, okay, I am at an accepting state. For example, in this second example, you are just saying that, okay, I recognize, I found the pattern then in the input. And there is going to be exactly one starting state that when your machine started working, it will be in that starting state. Here is this starting state. Next week, I am going to talk about the finite states and formally define it, and we will see lots of examples, so don't worry for now. Before I actually finished this part of the lecture that covers the introductory concepts, I just wanted to also introduce 2 terms, grammars and regular expressions. A grammar basically is, we are going to refer to grammars a lot. A grammar is going to be a set of rules that basically represent that's a language, how a language can be generated. So those rules will be something like, for example, this, that in, for example, in programming languages, in any programming languages, we would have a grammar for the language. Basically, that grammar tells us what what expressions can be generated. For example, the set of some rules for generating the arithmetic expressions like this, that basically they are going to kind of be the recursive definitions, that e goes to e plus e. So using this rule, you can actually generate some, arithmetic expressions like a, b plus c plus d or something like this. This is not complete, just wanted to actually tell you that how it works and how this is going to be some recursive structure using these grammars. And the other one is regular expressions. Basically, regular expressions are going to be some representation for regular languages. We will talk about regular expression for at least a complete week. I will come back to this one. This is also just some formal, this is something like a grammar, but with less power. So regular expressions are definitely less powerful than grammars, but they used to represent some a set of strings. They used to represent regular languages. So let me actually finish this part of the lecture, and in the second part we will just review some formal proofs.